Welcome. My name is Renee Clary, and today we will be investigating weathering and erosion and the formation of sediments. If sediments are deposited, cemented, and compacted, they can be lithified into sedimentary rocks, one of the three main rock types and involved in the rock cycle. As you might suspect, the rock cycle, sedimentary rocks, and weathering and erosion are closely tied to plate tectonics, another of our main themes. Weathering is a process that has greatly modified the surface of the Earth over the 4.6 billion year history of our Earth. So today we will be touching on all of the main themes in geology. Let's get started. What is the difference between weathering and erosion? Well, weathering involves physical and chemical processes that alter the surface of the Earth, and erosion involves the removal of those weathered materials. This diagram summarizes how sedimentary rocks are formed. We have weathering, erosion or removal of those sediments. They are transported via running water, wind, glacial ice. They are deposited in various environments, including rivers, deltas, beaches, glacial moraines, and then they can be lithified, compacted, and cemented together. What if we have granite, for example? How can that be weathered? Well, we can end up with fragments of that old granite pebbles and boulders forming gravel that can then be cemented and compacted together. We can also weather granite to get individual crystals of those original minerals, such as quartz sand grains, sand-sized particles. We can also produce new minerals through weathering reactions. We get clays, and these particles form mud-sized grains that can be compacted and cemented together. Chemicals can also be dissolved in solution, silica, sodium ions, to form salt and chert and other evaporites. So from the weathering of one rock type, granite, we get a variety of different sizes and types of weathering products. Here you see a photograph of the process of weathering, and as you can see in that picture, there are different sizes, and also it looks like altered material, clay, at the bottom of the granite outcrop. Weathering is the physical breakdown and chemical alteration of rocks at the Earth's surface. So, as you might suspect from that definition, we have two main types of weathering: physical weathering and chemical weathering. Physical, sometimes referred to as mechanical weathering, is disintegration. This is the breakdown of rocks into smaller particles. So let's go back to granite. If we have a big outcrop of granite and physical weathering occurs, we end up with smaller pieces of granite. They're still granite, but the pieces are smaller than the original parent material. There is no change in their chemical composition. On the other hand, chemical weathering is decomposition. It's a change in the chemistry, the makeup of the parent material. Let's first take a look at mechanical weathering or physical weathering. Again, we're only breaking down that big rock into smaller pieces. Frost wedging is a very important process through which mechanical weathering proceeds. Frost wedging involves the repeated freezing and thawing of water in fractures, and this widens the fractures. Now, why does that happen? Have you ever put a bottle of soda or perhaps a bottle of Gatorade in the freezer only to return to find that, well, your bottle split or your can split? Why did that happen? Well, when water moves to ice, when it crystallizes, it expands. Ice takes up about 3% more volume than water does. So when water percolates down through those cracks, guess what happens? Overnight, we may end up with widened cracks, and slowly the block will break apart. Now, talus refers to the accumulation of debris at the bottom of the mountains. This results from frost wedging. We get a lot of material that is broken apart by the action of water into ice, and this material accumulates at the base of mountains. Here you see a diagram, water in the fractures or joints of that rock, and what happens as that water freezes? Well, it expands and the rock slowly breaks apart. Here's an action shot. You can see the big blocks of rock that have been broken apart simply by freezing and thawing processes, frost wedging. And as that material accumulates at the base of mountains, we have a lot of talus. Once when driving through the middle of our country, I saw a Cathedral of the Plains sign in Kansas, and I decided to stop. Actually, I had 3 very active little kids in the back of the car, and I was looking for a playground to kind of burn off some energy. And I figured that anything that had the Cathedral of the Plains probably had a playland somewhere. Well, to make a long story short, what we found was this beautiful cathedral that had been built of limestone. And the way it had been built was that the wheat farmers during the winter had gone to limestone outcrops, and they had drilled holes in the limestone at regular intervals. Before they left for the evening, they poured water in those holes that they had drilled. They went home, had dinner, and returned to the limestone outcrop the next day. And guess what happened? Well, as the water froze in those nice bore holes, the rock cracked, and they used those limestone blocks to build this cathedral. Man-made frost wedging, if you will. Another type of mechanical weathering is organic activity. Now, we're not talking about chemical changes here. We're talking about how plant roots and burrowing animals can break apart rock. For example, that tree is growing and those rocks are splitting apart. There's no chemical interaction necessarily going on, but we're looking here at the mechanical action. Pressure release is also a form of mechanical weathering. This happens when granite or other rocks cool below the surface of the earth, deep below the surface of the earth, and there's a lot of pressure in their original environment. Well, as they're exposed through weathering and erosion to the surface, there is a pressure release, and in this pressure release we have sheeting. This results in what is known as an exfoliation dome. Here's an old great diagram that summarizes that. Look at the top. That granite batholith is several kilometers below the surface of the earth. But over time, millions of years, the overriding sediments or rocks are eroded away. And now that batholith is exposed. So there's a release of pressure and an uplift of the region, and sheeting results. And because it has split along these nice sheet lines, we have exfoliation. A very famous batholith undergoing exfoliation is Stone Mountain in Georgia. And finally, 2 other types of mechanical weathering. Salt crystal growth. If we have crystals growing in joints or fractures of rocks, these crystals can slowly widen those joints or fractures. And again, we're talking about a mechanical process. We're not necessarily talking about a chemical reaction at this time. Thermal expansion and contraction can occur, and it usually occurs in areas, or it has a more noticeable effect in areas where you have great variations in temperature between the heat of the day and the cool of the night, in a desert region, for example. What about chemical weathering processes? Well, remember, disintegration or chemical weathering results in a different product from the parent material. So not only are we looking at a smaller size being produced, but we're also looking at a totally different mineral or composition from the original parent rock. Solution involves dissolving out parts of the original parent rock. It is a very important chemical weathering process. Fortunately, the water molecule is polar and it attracts ions. I'll show you that in just a minute. Because it is a polar molecule, it has a positive end and a negative end. If solution occurs over a long period of time, we call this process leaching. And finally, the reaction of carbon dioxide in the atmosphere or in the sediments with water forms carbonic acid, H2CO3, which can then deionize or separate into the carbonate ion and hydrogen ion. And carbonic acid is an important process. This entire process is important because it results in the dissolution of limestone. So we can see caves created, karst created, and I'll show you another picture of that in just a second. Let's take a look at that polar water molecule first. Here you have a large red oxygen atom joined chemically with two hydrogen atoms. Now this is a covalent bond. It does not involve the complete transfer of electrons, but the electrons are shared. They're shared unequally, meaning that oxygen has more of the electrons held tightly than the hydrogens. So what happens is that this results in a positive overall charge at the top of that molecule in this diagram, the hydrogen portion, and a negative charge for the oxygen. Well, what does this mean as water moves through rocks and soil and other materials? It means that the negative part of the molecule, the oxygen, that big red oxygen, is attached to ions that are positive. For example, the sodium ions. The positive end of water, those hydrogens, are attracted to negative ions. For example, the chloride ions in the diagram. So the positive negative attraction will result in those ions being carried away in solution. We're changing the composition of that parent rock. This is a great photograph showing weathering along joints, natural joints of the rock. The water is percolating through those joints, and as you might imagine, solution is occurring along those joints more readily than it is occurring in the rest of the rock body. Now, in the case of limestone, dissolution, carbonic acid formation over time can result in huge caves, such as this one. In addition to the solution process, there is also oxidation. Oxidation in chemical weathering refers to the reaction of a rock with oxygen to form oxides. So basically we are causing the rusting process to happen. What would happen, for example, if you left a box of nails ungalvanized in your backyard over a period of time, rain, whatnot? When you discover your box of nails, you'll find that they've been rusted. Well, the same thing occurs in the rock record as well. Here you can see a close-up and personal view of a rock that is slowly being oxidized. Look at the orange-red color along the base of that little pebble there, and you will see oxidation in process. Oxygen is being reacted with the iron in that rock, and we are getting an iron oxide product. Okay, so we have solution, oxidation. We also have hydrolysis. Hydrolysis occurs when the ions of water substitute for ions in rocks, and this results in the breakdown of rocks to clay minerals. Here's a great photograph showing the breakdown of granite, the chemical weathering of granite to clays. Now, we've just discussed chemical and physical weathering processes, but is there anything that can affect the rate of these processes? Well, not only is there anything, there are several factors affecting the rate of weathering, both chemical and mechanical. Surface area is one of the big ones. Here we have the same volume of material, but with different surface areas. Note what happens when we take that it's a 1 meter cube, and we have 6 square meters of surface area exposed on the left-hand side. If we divide that into 2, 4, 6, 8 blocks instead of the one big block, we've now doubled our surface area to 12 square meters. If we break it down again, we now have 24 square meters of surface area. Surface area is important because this will increase the amount of the rock exposed to ice action, frost wedging, to water for dissolution processes. So the more surface area exposed, the greater the rate of weathering. High temperatures. As you might suspect, there is a slower rate of weathering in the Arctic than there is in the tropical region. High temperatures tend to accelerate weathering processes. And here you see a summary graph. Note that not only does this graph look at temperature, and that is on the y-axis, cold at the bottom, all the way to hot climates up at the top in centigrade degrees. You also see this is plotted against the precipitation, dry climates versus wet climates. And you can see that cold, dry climates have minimal weathering compared to hot, wet climates. So again, liquids, or the amount of precipitation, also influences the rate of weathering. Type of rock is also important. If we look at the stability of silicate minerals, we see that olivine is the most unstable at the Earth's surface, followed by pyroxene, amphibole, and biotite. In other words, olivine is most readily weathered, and biotite in that group is more stable at the Earth's surface. Now, why does this order look familiar? Olivine, pyroxene, amphibole, and biotite. Well, remember Bowen's reaction series? If we looked at that discontinuous branch, that reflected the order in which the minerals crystallized in the melt. Olivine crystallized at the highest temperature, followed by pyroxene, amphibole, and finally biotite as that magma or melt slowly cooled. And remember also that Bowen's discontinuous series also reflected the arrangements of those silica tetrahedra. So olivine is formed from single tetrahedra, whereas pyroxene is a single chain, olivine is a double chain, and biotite mica is a sheet silicate. So of those four, the sheet silicates are more stable at the Earth's surface than olivine. There are several effects of weathering. Spheroidal weathering, for example, results because of surface area. The corners of a rock, if we have a rock block, are attacked on all three sides. Whereas if we have a plane where the rock is flat, we only have attack on one side. Edges are attacked on two sides. So basically the corners weather fastest, the edges weather second fastest, and the flat planes of the blocks weather the slowest. So the sphere is the resultant shape. It's the most stable shape. And here we see that occurring. Note that the blocks that are exposed to more water activity toward the surface are rounded. And there we go, another picture of spheroidal weathering. In addition to spheroidal weathering, another effect or result of weathering is soil. Soil refers to the accumulation of weathering products on Earth's surface. Now, you may recall from the introduction that regolith refers to the broken pieces of rock and sediment at the Earth's surface. Not all regolith, however, is soil. We also have humus, that organic material that results from the decay of plants and animals. And we also have water and air in the soil. Soil formation, or the types of soils, are affected by climate, relief, and rock type. And this diagram shows you a general overview of soil. We have mineral particles, we do have air and water, so it's important that soil not be super compacted. Organic material, the humus, about 80%. Excuse me, humus is 80% of the organic material, which of course is 5%. I don't want to mislead you on that. This diagram shows a profile of the types of soil, the soil depth, as related to the precipitation, as related to the altitude as we're moving further up north versus toward tropical regions. You'll notice that in the Arctic region toward the right-hand side of the graph, we have very shallow soils. We don't get great soil formation in that area. Whereas in temperate regions, we do tend to get pretty good soil formation. If we have low precipitation, however, in desert regions, we have very, very shallow soils. We don't get good soil formation here either. But look at the depth of soil formation. Look how quickly soil can be formed in tropical regions with good precipitation in warm climates. We can talk about soils by describing the different soil horizons. These horizons are the layers of a soil from the top, the Earth's surface, downward. We're looking at a soil profile. First off, we have the ozone, not to be confused with O3, but the ozone, or the O horizon, is the area where we have the buildup of organics, and this is where humus is found. It may or may not be present, depending on how many organics we have in the area. That's followed by the A zone, which is the zone of leaching. This is where you find topsoil. There's intense biological activity in the A horizon. Next, we have B. The B zone, or the B horizon, is the zone where minerals accumulate, and we'll look at that in a little bit more detail in an arid environment. This is the subsoil of your soil, and this is where we commonly find ore accumulating. We have a C zone, which is partially disintegrated bedrock, and that will rest up against the bedrock. Here is a graphic depiction of that. Notice how thin that O horizon is. Of course, depending on the location and the amount of precipitation and the temperature, the width of these zones will vary quite a bit. Here you see an A zone, or a zone of leaching, and this is where water infiltrates through during a rain. It soaks through and dissolves out the minerals in the soil, so this is the zone of leaching. If there isn't enough water to completely remove those ions or atoms or molecules away from the system, we get accumulation in the B zone. This is the subsoil zone. And moving down farther away from the surface, we see the partially disintegrated bedrock, and then we have a gradational contact, and then we're up against the bedrock. There are different types of soils, as you might imagine. We're only going to briefly look at 3 of them. And again, this is a very, very generalized view. If you ever take a class in renewable resources or in the College of Agriculture, there are entire semesters devoted to soil types, and many, many, many different types of soils that are studied and are further classified. The 3 basic ones we will take a look at are the petalfer, the petachal, and the laterite. Petalfer has aluminum and iron content, and you'll note that I wrote petalfer using the symbols for aluminum and iron. And this is an easy way to remember this. Petalfer, the word, includes the symbols for aluminum and iron. Petalfers form where water is abundant, and most minerals, therefore, are leached out of that horizon A, or the A zone. We see a lot of organics in petalfer soil. Here is a typical petal-fir. You see conifers growing. Again, there's plenty of precipitation compared to a more arid region. The water will percolate down through that A horizon and leach completely the minerals out of the A, and actually there's enough water to carry those minerals out of the B horizon as well. Well, what about in cases where we don't have a lot of precipitation? For example, where we can wash some of or dissolve some of those minerals out of the A horizon, but we just don't have enough water to completely remove them from the system. We get the formation of a petal cow, where there is less intense chemical weathering or in arid environments. The calcium carbonate and petacal, you can think of calcite or calcium carbonate, the calcium carbonate precipitates in the B horizon. So it is dissolved out of the A horizon, but it reprecipitates in that B horizon or the B zone, and it results in these nodules of calcium carbonate referred to as caliche. Again, this occurs in a very arid environment. Notice the cactus, and notice how thin that soil is. That O horizon, where we have the organic material, look how very thin that is in that diagram. It's practically just a little black line. The A horizon is also very small, but the B horizon is better developed, and we do have reprecipitated calcium carbonate in that B horizon, or caliche. And here is a photograph of caliche. Very arid soil. Okay, and last but not least, we're going to cover laterites. Laterites form in the tropics, and this is because we have very intense leaching. There's a lot of water moving through the system, so we're dissolving everything out of the soil. Even silica moves out of the soil. Quartz is dissolved and moves out of the system. So a very wet climate. We do have an O horizon, we have a developed A horizon and a B horizon, but unfortunately all the minerals are being carried out of the soil. We have a lot of precipitation, a lot of water moving through the system, so as a result these aren't very fertile soils, and that's why we see slash and burn agriculture occurring in the tropics. The soil fertility simply is not there. Over time, this is the type of soil that results. This is a laterite soil, and the inset picture at the lower right is a picture of bauxite, and I have a hand sample here to show you as well. Bauxite is the ore of aluminum, and this is what forms with very intense chemical weathering. Again, even the silica is taken out of this system, and so the aluminum is not very soluble, so it accumulates. So this is bauxite. This is what's mined for our aluminum ore. Now what's neat with a laterite soil is that it can harden and form these clay-like bricks or building stones. And the Khmer Empire in Cambodia used laterite blocks or stone blocks in their temples at Angkor Wat. I had the privilege of being in Cambodia not too long ago for a conference, and I had to steal away to see some of the architecture here from the Khmer Empire in Cambodia, and the building blocks are made of laterite along with some sandstone that was transported obviously from another source. There's no sandstone in the area. Okay, unfortunately, we can have some problems that result with some soils. Expansive soils, sometimes called shrink-swell soils, result because some clay minerals will increase in volume when wet and decrease in volume when dry. So they expand and then they contract. And this occurs, clay minerals or sheet minerals have areas between them where water can move into the layer if the attraction between the layers is not strong enough. So in other words, if we have a large positive and negative charge between the layers and the ions that are between the layers, generally water can't move into the layer. But when we have weak attractions, water can infiltrate between those layers and the clay expands. And then in times of less precipitation or in dry climates, those soils will shrink. Structural damage can result. And here is a photograph just showing you, look at the uplift of the sidewalk there. No, the builders, the construction workers did take pride when they first poured the concrete and they had it level, but over time shrink and swelling of the soil underneath has produced that uplift. And you can imagine what happens in areas with houses and foundations and gas pipes that are coming in through the foundations. Can cause a lot of structural damage and result in loss of life even when these gas lines break. Now, unfortunately, soil formation is a very slow process. It usually requires hundreds or thousands of years in arid environments for soil to form. Soil can be degraded by erosion, by chemical deterioration, and by physical deterioration. Chemical deterioration would result from the loss of minerals and nutrients as soil is formed. We have a physical deterioration that would result from compaction of soil, so we lose the pore space where the water and the air are found in a soil. And this can result when we have a lot of animals, for example, in an area that are very active and compacting the soil beneath them. So soil can be degraded. Now, in the United States alone, we lose soil to erosion at the rate of 13.9 metric tons per hectare per year. So this can be a serious problem, and as a result, we need to think about our activities and employ sound agricultural processes so that we can maintain our soil. It is a natural resource, and unfortunately, it is very, very slow to form. Well, that will conclude our section today on weathering and erosion. I'll leave you with this picture of a very eroded landscape, a very degraded landscape with soil. And I thank you for joining me. If you have any questions about any of the material, please feel free to post them on your discussion board or email your instructor. Have a great day.